Hello, and welcome to your last lesson on higher mathematics statistics. Last lesson on statistics before we move on to probability, and we're going to be looking at frequency tables. It's a particular type of presenting data and graphing it. We're going to be looking at two different types of graphs. Tends to be the trickier parts of GCSE statistics here, so I thought it would devote a lesson to this specifically. So we can look at frequency tables, what they are, why we use them, what are the pros and cons of using them. We can then look at grouped frequency tables. What does it mean to group our data, and how do we group it? Why do we group it? And what limitations does that put on us? When we're trying to calculate statistics. So then we're going to look at cumulative frequency. What does it mean to accumulate frequency? Why do we do that? Um, and how do we use that to do a cumulative frequency graph, which is often what we're more interested in. And that serves various purposes that we can't get just from the tables. And then finally, we can look at histograms. Probably the trickiest graph to work with, but it's not too bad, um, which is really useful for grouped data. Uh, so let's take a look at that. So we're starting off with frequency tables. So a frequency table, it's a way of collecting data that works well when we have a limited number of values. So it's certainly if we're taking like a large, uh, number of data, like a large frequency of data points, you're going to get a lot of repeat data. So we collect it together into a table of the different categories. So we have two columns at a minimum in our table. The categories of data that we're collecting, and then the frequency in each of those categories. So here, maybe we have like some kind of estate agents or property developer or whatever, and they've got a certain number of properties, and we're tracking how many bedrooms are in each one, going from 0, 1, 2, 3, 4, 5. 0 being essentially like a studio flat, uh, and then we've got 1 bedroom flat, 2 bedroom flat, or house. And here's the frequency that fall into each category. So we can then recover the original data if we wanted to. Really, we want to be able to calculate statistics directly from the table, because often it's um, it wouldn't be practical to actually write out data, certainly if there's a lot of data, and um, yeah, it would just take too long doing that way. We want to be able to more just visualize in our head what the data set would look like. But for this example, at least, I've shown you here. This is what the original data set would look like. So you see, we've basically got 7 zeros, and then we have 46 ones. 29 reported 2, 11 reported 3, 6 reported 4, and then 1 5 right at the end. So this is like what the original data set would look like, and here's how we've just brought it all together into a frequency table where it's much neater and more concise. But we need to know how to calculate statistics, from that table. So minimum value, maximum value are quite easy to read off. It's going to be the 0 and the 5. The median, so that's going to be the middle value. So if you add up all that frequency, we then will know how many data points we've got in total. So you'll find it's 100 data points. And so we need to find where is the median. So the median is the 50th data point. So if we've got these in order, so 0, 0, 0, 0, 0, then 1, 1, 1, 1, 1, and so on, we find where is the 50th data point. You don't really want to go through all that data there. If we look at the actual frequency table itself, so we see 7 is 0, and then by the time we get to the end of category 1, well, 1 bedroom, okay, that's then going to have been a total of 53 data points. So we can see that 50th data point is going to be in category 1, 1 bedroom. So therefore, the median is going to be 1. So this is a common mistake see people make, is it's maybe they'll take the median of those frequency numbers, or maybe they'll start averaging those frequency numbers. That's not what we want to average. We want to average the actual data set, but the data set we haven't explicitly got it there. The data set is that block on the left. This table is then just showing how much of each data point we've got, and so we need to infer from that what our particular different statistics are going to be. So lower quartile, sometimes ones like this where you've got a very small data set, like small number of categories. sometimes and it all might be quite tightly clustered around one area. Like here, uh, most of them are either one or two bedrooms. I think it's like something like 75% of them are one or two bedrooms. And sometimes you'll find that the median and the lower quartile will then be the same value. The upper quartile we find is two. So, okay, lower quartile is the 25th value. So we can quite clearly see that's going to be in the one bedroom category because it's not going to be in the first because there's only seven there. And then by the time we get to the end of the one, we're up to 53. So it's definitely, the lower quartiles in there. Once we get to the end of the category two, we're now up to, uh, what are we up to? 82, if I've got that right. So we're just adding 29 onto that 53 that we had. So we can see by that point we're definitely past the 75% point. So I've done a frequency of 100, so the 75% point is just 75. But if it's not 100, say if it was like 1,000, then the 75% point would be 750. So we need to be aware of that. That's where the quartiles correspond to 25% point, the 50% point, and then the 75% point, through our data once you've got it ordered like this. So that's how we'd read off our statistics. Those statistics for say the mean, like the geometric mean specifically. First of all, we need to get a sum of all the data points. And then we can divide by the total number of data points, which we know is 100. Adding up the frequency is 100 data points. So obviously we don't want to add them up from the actual raw data, doing 1 plus 1 plus 1 plus 1. We can do this more concisely by multiplying the number of the frequency by then the number of bedrooms. So here we've got 7 lots of 0. Then we've got 46 ones, we've got 29 twos, we've got 11 threes, 6 fours, and 1 5. So by doing that multiplication and then adding up those, we can then just get the sum more more efficiently. And so if we do all those multiplications, we get these values and we add them all up and we get a total of 166. So this value is like the total number of bedrooms really across all the properties. And then, okay, now we're basically dividing by the total number of properties. And so that will give us the average number of bedrooms per property, which comes out to 1.66. So when we're doing a geometric mean, arithmetic mean like this, even though we're dealing with integer values like bedrooms, like you can't have 1.66 bedrooms, your mean can still come out to a fractional value, and that's okay because it's just kind of like a general midpoint in the data. It's not like we're not talking about saying that they actually have 1.66. It's just on average it's that much. So it's somewhere between 1 and 2. Most of them are right between 1 and 2, but slightly closer towards 2. Um, so that's basic grouped table data. So yeah, you don't want to list all the data out like that, but you want to be able to kind of visualize it in your head. So then when you're calculating your mean, your median, you can then think how you can do it using this data in the frequency table. And I've given you examples there of how we would do that. So let's move on to grouped frequency table. So this is something like this. So say what we're tracking here is the time spent on a website. Like, so a site is tracking the frequency of people on their website and how long they spend on their website. So we might have something like this, where T is the time spent on the website, and we have between 0 and 2 minutes, 2 and 4 minutes, 4 and 6 minutes, and just like with we saw when we was doing our questionnaires in the first statistics lesson, we need to be careful that we make sure we don't have overlapping categories. So you see here, we've done it using inequalities, and you see how we have 0 up to and including 2, and then we have specifically greater than 2, but up to and including 4, then specifically greater than 4, up to and including 6. So if we had one that was right on the boundary, like someone who spent exactly 4 minutes on the site, we know exactly where to put that. It would be in the second category, 2 up to 4 minutes, up to and equal 4 minutes, you can see. So there's things like that. You might always get asked questions like that where if the categories aren't right and they might ask you, okay, what is wrong with these categories? That could be something that we could have, or perhaps something that includes all the data. Like say that last one, we've got 15 up to 30 minutes. If we know no one spent more than 30 minutes on the website, then that would be fine. But sometimes that last category, maybe you want just T greater than 30. Just to make sure you're then including any outliers that are beyond that point. But for this example, I'm just assuming that no one spent more than 30 minutes. So we can then have the frequency of people that fell into each category. So you might have a whole bunch of people, um, maybe 6,248 were somewhere between 0 and 2 minutes. So we don't know where they could be. Maybe uh, you'd have one that maybe it was a minute, one that was 40 seconds, one that was 32 seconds, one that was a minute 47, so on and so forth. They would all be grouped together and put into that category. So that's what it means by grouped data. So rather, sometimes you have cases like this, especially when you've got really large really large data set, and we don't really need each individual data set. What we do is we group them up into meaningful categories, and then just put them in the category that applies to them. So we can calculate the total frequency still, because okay, the total number of people that was tracked over this time period is going to be 32,696. And then we could find, first of all, which category the quartiles will be in, say. So the median, if there's 32,696, the median is the 50% point, the midpoint of the data set. So you see, once we had the small data sets before, we could kind of just count along and find the midpoint. Now we need to sort of think more abstractly in the general sense. When we've got 32,696, if we half that, okay, then it's going to be the 16,348 value is going to be the median. Okay, where does that value lie? So we know it's not in the first category because there's 6,248 in the first category. If we then look, okay, in the second category, that's another 7,256. So approximately that takes us up to about 13,500. The next category is then just over 7,000. So we can see that's going to take us to over 20,000, the 20,000th person. Because you see, this is ordered, isn't it? The categories they're going up, and so it's we can calculate the median doing that. And so we can see it's in that category of 4 to 6 is where we're going from like the 13,500th up to the 20,000th person. Well, we can see the 16,348 is going to be somewhere in that category, so we can identify the category that the median is going to be in. Likewise, the lower quartile is then going to be the midpoint between 1 and 16,348. So it's going to be the 8,174th value, and we can tell that's going to be in this category because it's not going to be in the first one because that's just about up to the first 6,000 or so. Then if we include then the second category, that takes us up to the 13,500. Okay, you can see we've gone past the 8,174th value. So we can see it's going to be somewhere in that category. And then likewise for the upper quartile, it's going to be this. So the seventh, you remember it's the 75% point. So we take the total frequency, 32,696 and find 75% of that. And so, you see these broad categories, they encompass like thousands of people. We only just need to be roughly, so we're seeing like, roughly 24,500. Where is that point? So we knew by the end of the third category we was up to about 20,000. By the end of then the next category, 6 to 9, that's going to take us up to about 26,000 or so, 26,500 perhaps. So we can see we're going to hit the 24,522nd value somewhere in there. So we can see the upper quartiles in that group. So you see through, thinking it through like that, and you see the data is ordered, even though we don't know what the exact data is, it's just kind of grouped into these categories. We can still infer when the 25th percent is going to be, when the halfway point is going to be, when the 75% point is going to be. And we can identify the groups that those quartiles are going to be in. Right, so if we keep our total frequency there, And now say if we're trying to calculate the geometric mean, so not geometric, the arithmetic mean, sorry, so just the regular mean, we it poses a bit of a problem because we need to add up all the data and then divide by the total amount of data, which is we can divide by the total amount, which is 32,696. We know that exactly by tallying up the frequency, but we don't know what the sum of all the data is going to be because we don't know the data, and all we know is the categories they're in. So we've got 6,248 people that are within the category 0 to 2, but we don't know where are they in that category. They could all be like close to 0, or they could all be close to 2, or somewhere in between. So what we need to do in order to calculate the mean, we need to pick a single value that can be representative for each group. And we want to pick sensibly so that we can minimize the errors we're going to make. Because so this is only going to be an estimate. When we've got group data like this, we can't get the exact data, the exact value of the mean. We need to just estimate. Um, so where do we put that representative value? So you see that first category between 0 and 2. Say perhaps we pick the value 2. The problem is with that is, say if all the data points are down the left end, well then we could be as much as 2 minutes off the correct values, which is a problem. Like that could be potentially quite big errors we're getting. So maybe we go down the other end and we take 0 as the representative value of that group, but the data could equally be nearer the upper end, and again we could be as much as 2 minutes off the true value. So what we do is we take the midpoint of each group, because that way, if the data is nearer the lower end, or if it's nearer the upper end, or it's somewhere like in between, it's like evenly distributed perhaps, um, we're minimizing the maximum possible error we can make on each data point. Like each data point, we can only be as much as 1 minute off now if we take the middle point. So that's what we do. For each category, we take the midpoint. And what we do is we now treat it like a regular frequency table. We assume all the data for the first 6,248 people, we assume they're all 1 minute. Then for the next one, 7,256, we assume they're all 3. We just take the midpoint, and this will get us the most accurate answer, or the best chance of getting the most accurate answer, which is all we can do really. So the sum of all the data is going to be approximately equal to this. So we're just multiplying this up the same way we did with the previous one and add it all up, and you get this big number. So this is like the total number of minutes spent on the site across all the people. So a lot of time there. And then we divide it by the number of people, which will get us then the average amount of minutes per person spent on this site, which comes to just over 6 minutes. And again, yeah, you see I've put a squiggly there. So squiggly equals because it's just approximate. This is not the exact average. It's just the best estimate that we can get. So now let's look at cumulative frequency. So we understand what frequency tables are, grouped frequency tables. So frequency tables are relatively basic. For cumulative frequency and grouped and histograms, we tend to be using grouped data more. So we might have something like this and say, so imagine this is like a different site, maybe a competitive site or something like that, and we're comparing the two. And you see this one, they're got the same thing, but you see the categories are a bit different. We're checking from 0 to 5, 5 to 10, 10 to 15 minutes, and then we've got the number of people that spent that much time on their website. And then what we want to do is we want to calculate a cumulative frequency. So cumulative means, to accumulate, like you keep adding on the next frequency. So the first one is just going to be the same. Then what we do is we add the 3,549 to the 1,625. And then we add the 7,922 on top of that. And then we add the 8,231 on top of that, and so on and so forth. And that's a cumulative frequency. And so then once you get to the end, the 29,164 is going to be the total frequency. And if we wanted to plot this on a graph, so you see there I've got the cumulative frequency in thousands. So sometimes you got to make sure you're mindful of what the units on the graph is. This is well, it's not a unit, it's just thousands. So rather than having to put 4,000, 8,000, 12,000, we can just put 4, 8, 12 and keep it a bit neater. And then time in minutes along the right, the bottom axis. So how we would actually plot this, we plot coordinates, and the coordinates, so vertically, it's just going to be the cumulative frequency. So you see this first value is about, 1,625, but in the x direction, what we plot essentially the midpoint, just like we saw with the mean. The midpoint is taken to be representative of the group. So we put up the time on the x coordinate essentially is going to be 2.5, and then for this next one it's going to be 7.5, and the cumulative frequency is then 5,174. And so you need to go through and plot. Obviously, for a graph like this, it's only rough. We can't plot it exactly because we're dealing quite big numbers. And when you plot a cumulative frequency, generally you'll get something like this, which is known as an S curve, for the reason that it looks vaguely like an S. So this one is a bit uh, like it's not so curvy. Like some S curves can be very curvy. Um, and the reason why that is because most data sets, generally you have most data collected around the middle, and then you gradually get less as you go out to the really high and low values. This is what's known as a normal distribution, which we don't really study much at GCSE level. But if you go on to A level, you'll be A level math or statistics. You're going to be you'd be studying normal distributions a lot, and so that causes this characteristic shape. Where it goes up steepest in the middle because that's where most of the data is, and then gradually less steep towards the top and the bottom where there's less data, and so it creates this S shape. Um, so now let's do the same thing for the other data set, the first data set that we had. So we're going to calculate the cumulative frequency again. So we get, 6,248 first. We add the 7,256, add the 7,102, and so on and so forth. Um, and then plot these points, being mindful that the midpoints, you might notice they're not so like horizontally, they're not evenly spaced like with the pink ones. Because if you notice those groups we've got, before the groups were equal. They were just 0 to 5, 5 to 10, 10 to 15. They were all 5 wide. Whereas you see this one, the first 3 groups are 2 wide, then 6 to 9 is 3 wide, 9 to 15 is 6 wide, and then 15 to 30 is 15 wide. So you see it starts to get a lot wider. And there's some reasons why you would do that. If perhaps you don't need many categories higher up because maybe there's less people there. Like we see here with the frequency, like even though we have smaller categories near the bottom, the frequency is still a lot higher than say the 15 to 30 category, a much wider category, but yet we have far less frequency in it because there's just far fewer people that are on the site for that long length of time. And so you see with this one is an example of one where that S curve isn't so prominent. Because here we've got an example of like a skewed data set where there's a lot more people down the lower end, not spending as long on the website. And so it's steeper early on and then gradually, settles out as it goes to the top. So, um, and you see that they finish up at 2 different heights. So there's not the exact same frequency here. Typically you might have the same frequency to easily compare them. So okay, that's how we plot a cumulative frequency plot, and it's good because we can kind of then see the overall data. But one of the key things we're doing is it allows us to estimate things like the quartiles more accurately, because before all we could get it was to the nearest group, which certainly if we've got some wide groups, that's not particularly useful. We want to try and get an estimate for the exact value for a median or the quartiles. But when we haven't got the actual data set, we can't do that. So we estimate from a graph like this. So, for example, we've got the total frequencies of each, and the median for, say, the pink one is going to be at the 14,582 point of the cumulative frequency. So what we do is we find that on the y-axis, and we read across and then read down, and that will give us an estimate for then the median, which will be about 13.9 minutes. So this is a great way to then get an estimate for the actual value of the median, not just the category that it's in. And then we can do a similar thing with the lower quartiles. Again, it's going to be the 25% point, the 75% point. We can calculate what value in the cumulative frequency that's going to be. 7,291 and 21,873. We can just read across until we hit the graph, go down, and it will give us the corresponding time that represents that point. So that then allows us to estimate the quartiles. And so yeah, that's why I keep using the squiggly equal sign, because these are just approximations, um, because we don't have the actual data points there. All we've got is we're estimating from this graph. So from one point to the next, we're just estimating by roughly drawing a curve through it. And so that gives us an ability to sort of see where would the data be between these points that we've actually plotted. The technical term for something like that is what's known as interpolation, if you fancy looking up more into that. But that's the use of drawing a cumulative frequency graph. And we can do the same thing for the green one. We can see the median is a lot lower, and the quartiles, if we read across to those, are also a lot lower, because we see that the data was a lot more front loaded. So yeah, so we get actual accurate times for how long people were spending on each of the uh, the sites there. So right, let's move on to histograms. So what is a histogram? So a histogram, it looks kind of like a bar chart, but the widths of the bar charts aren't all the same, and it's not like distinct categories like we had before. Remember with the ice cream shop that was looking at different flavors, and we had the flavors listed. Um, the x-axis is going to be actual quantitative values, and it can be continuous values, and the width of each bar is then going to be the width of these groups these groups that we have. So, and what we have is the we don't have the height of the bar being the frequency. We have the area of the bar represents the frequency, and there's a reason we do that. But let's actually calculate a histogram for starters. So first of all, we need to calculate what's known as the frequency density. This will then be the height of each of the bars. So what we do is that frequency, what we do is we divide it by the width of the bar. So this one, it's going to be between 0 and 2. So the frequency density is then going to be 3,124. Same thing with the next one. The width is also going to be 2. So if we divide 7,256 by 2, we get this value for the frequency density. And we can continue down. The next one will be divided by 2 as well. Then the one between 6 and 9, we're doing 6,234 divided by 3, because the width of the bar is going to be 3. The width of the next bar is going to be 6. So we do 4,176 divided by 6. And then finally, last one is 15 wide, isn't it? So we do 1,680 divided by 15, which gets 112. So that gets us the density. And then we can start plotting that on here. Like we have the frequency density on the vertical axis and the time in minutes on the horizontal axis. And we plot the first one. So the first one's going from 0 to 2, like the width of the bar is 0 to 2 minutes. And then the height goes up to 3,124. The next one is also 2 wide, going up to 3,628. The next one is also 2 wide. Then the next one along, you see how the bar is actually a little bit wider now, because it's 3 wide, and the bar goes up to 2,078. The next one's even wider still, and then the last one's very wide but very short. And when we have something like this, it allows us to kind of see the distribution, and we can kind of plot like a almost like a line of best fit through it. And sometimes what we would even do is try and calculate an equation for this line. It's not something you do at GCSE, but then it's almost like you'd have then an actual equation relationship between the time and then the number of people that spent that much time on your website, say, for this example. So, right, so the key thing here with a histogram is that the frequency in each group is represented by the area of the bar. And yeah, that's important. And then So then the height is then the frequency density. So you can think of that in terms of like we learned about density before as being like mass over volume. And so it's like how densely packed is that mass um inside that volume. If the density is very high, then it means there's a lot of mass packed into that volume. If it's quite low, then it's not so much mass. And it's kind of like here, but we're talking about frequency density. So within each category, we're um uh we're looking at how densely packed is the frequency in each of the little windows. So you see the earlier windows, they're very short windows, and we can see the frequency is very densely packed into it. And then later on, um, the uh, the thinnest bar, right at the end, we can see it's not very packed at all, because even though it's very wide, the overall area is still quite small, because the density is so low. Like, we have very few people in the 15 to 30 minute time. And that's what then kind of reveals the distribution here, um, because the area under the curve, under this curve we have, represents um, the total amount of data. So that is how we plot a frequency and a histogram, and the uses of it. We can observe the distribution like this for say continuous data, which we couldn't do with a regular bar chart. We can try and plot the same thing for the other company we was looking at, the pink one, and we can calculate the frequency density in the same way. It's going to be easier this time, because we're just dividing each one by 5, because the categories are all the same. And so you see here, if we plot it, we're going to get um, something akin to more of a regular bar chart, where all the bars are the same, but this is still technically a histogram. Um, and again, we could draw like a little curve like this, showing the overall kind of distribution. So there are some times when you might want to do this, like if your data is kind of more evenly spread out, or the other one we saw when we have different sized categories. Now, one last thing to finish up on. This is a very common type of question I see on histograms, and it can trip people up, and you want to make sure you know how to do this. So it's kind of like testing how well do you understand like how a histogram is plot. Um, and the key thing is remembering that the area of each bar corresponds to the frequency of people or things in that category. So, say if we're given this information that there were 2,036 people who visited the website for 25 to 30 minutes, we need to use this information to estimate the number of people that visited the site from 15 to 20 minutes. But you see, the problem is that we have no points on our vertical axis. So how on earth can we read what this graph even means? So look in the 25 to 30 minutes, that's the last bar in this histogram. And we can see that's 25 to 30. So the width is 30, and the number of people in that category is 2,000. Sorry, the width is 5, and the number of people in that category is, we've been told, is 2,036. So we know 5 times the height is going to equal to 2,036. So therefore, if we do 2,036 divided by 5, that will give us what the height is, which would come out to just over 400. So we can see that 2 boxes here on this vertical axis is going to be 400 people, or 0.4, because we're measuring in thousands. And once we've got that, if we know 2 blocks is 0.4, we can then just go on and put in the entire y-axis. Every 2 blocks is going to be 0.4. So great, we've now deduced what the axis is. We can now use this to read off what is going to be the value in the 15 to 20 minute category. So you see that's the one near the middle, the tallest one. And we can read off the height being around about 1.7. And so that's 1.7 thousands though. So that's actually 1,700. And we can times that by its width, which is 5, because remember, the frequency corresponds to the area of the bar. So we do the height, which is 1.7 times 1,000, and the width, which is 5. So times that by 5, and we get 8,500. And so that's an estimate for how many people are in that category, which isn't exactly right, but it's an estimate of how many. Like, it's limited by how well we can just read off the graph. So let's leave that there. So that's the end of statistics. lot of statistics really useful, really powerful tool. If you can get very good at it, it's a great career choice to go into any statistics related field. So I guess I'd leave you end this statistics um, lessons with a caution about statistics can sometimes be misleading. The mistakes can be made, or sometimes they can be deliberately misleading. So got to be careful with that. And here's some examples of weird correlations sometimes we'll see between things when there's actually no causal link. So here's like one example, like the between divorce rates and margarine consumption. This is real data, by the way, and you can see that it looks like there's a correlation between the two. But obviously, what would be the link? There's no real causal link. Like here's another example between consumption of cheese and revenue generated by golf courses. Here's another one between honey production of bee colonies and then arrests of juveniles for carrying marijuana. There seems to be like an inverse correlation here. As the honey production goes down, the juvenile arrests go up. But then, what causal link would there be? The answer is that there isn't. There's just this has just happened by chance. And if we go looking for things, sometimes you can try and you can see patterns when there's no actual link. So that's something we've got to be cautious of with statistics. Things like this can just sometimes happen by chance. And speaking of chance, next time we're going to be moving on to probability. So far we've been trying to calculate things exactly. Sometimes we've been approximating things. Um, so when it's still a true value, but we're approximating that true value. Now we're dealing with probability. So that's when we're like, there's just a chance of something happening, a chance of it not happening, and we want to see how can we calculate that for various different events. So that's I'll see you there next time for work on probability.